So we're going to start 6-1 with graphing, and when we come back on Wednesday, we're going to pick up with modeling. So exponential models are actually really useful to us. A lot of real-world scenarios will follow exponential models, but the reason why that works may make more sense if we first kind of understand a little bit about the graphs. So I have a note there at the top, like what makes something exponential? The variable is in the exponent. Oops, sorry. So these are things like y equals 3 to the x, y equals 1/2 to the x, y equals 5 times 2 to the x. And if you're thinking about the chapter we just did, they kind of remind us of the geometric sequence, because it had the rule a sub 1 times r to the n minus 1. So remember how like every time we saw the arithmetic sequence, the dots that represented terms looked like they were lying on a straight line. And then every time we saw the geometric sequence, if the ratio wasn't negative, they sort of followed this little curve. That's the shape we're going to be seeing. Now, we can say that exponential functions have the form y equals a times b to the x. B is the base, and that makes sense in terms of like vocab with exponents. The thing that's being raised to the exponent is called the base to the exponent. And of course our variable is up in the exponent. Okay, now there could be some number out here, and we're also going to see later on in the chapter in section 6.4, we're going to put some other numbers to shift our graphs, but this is like a basic graph. And the simplest exponential function, and my abbreviation for exponential and exponent is just this because I'm too lazy to write the whole word. Okay, the simplest exponential function that you're going to be working with today is just this. Y equals the base raised to the exponent. So we're going to start off pretty easy, pretty low key right here today. Just b to the x. Now, exponential functions can be classified one of two ways. They can be exponential growth or exponential decay. How will you know if it's exponential growth or decay? Based on the value of the base. So when the base is greater than 1, it's exponential growth. Just looking at b. When the base, I should do it like this, the base is less than 1, but also greater than 0, it's decay. So based on those two things, what has to be true or what cannot be true about b for exponential functions? B cannot be negative. B cannot be 0 or 1. Okay. So like we did see some geometric sequences where the ratio, which would have been like our base to our exponent, was negative. That's allowed in sequences. Totally fine. And I think we even graphed one on our homework. It was really weird because like the first term was in the positive section and then the next term was negative. And then it went positive and negative. So it didn't look like the other graphs did. Okay? And that's why that's not exponential. So in order to be exponential, it has to be positive, and it can't be 0 or 1. 0 and 1 would be really boring, right? It's always 0 or it's always 1. Horizontal lines. Okay, now in addition to being called the base, like the base of the exponent, is also called the growth or decay factor. So this is really important in terms of directions. I make sure I write this down, maybe bubble it or underline it or write it in a different color, whatever you like to do, so that when you see that in directions, if they say identify the growth factor, identify the decay factor, you know that your answer to that is just the value of B. The value of B is the growth or decay factor. Okay, so have a conversation with your pod mates. You do have new pod mates, so if you want to introduce yourselves really quickly, you know, in case you think anybody doesn't know your name, let them know your name. Decide if the function is growth or decay with your pod mates. I'm going to call on people randomly, so make sure you have an answer for all four. Talk to your people around you.
Okay, I'm Nathan. The one to the left, the growth, the one to the right, decay. Yep.
My name is not Ronaldo. It is Jackson.
Does that happen?
No, but I want my last name to be Ronaldo or Reynolds.
Wait, the last name's Jackson or first name?
My first name's Jackson. My last name's Reynolds. But if it was Ronaldo or Reynolds, would that happen?
Yeah.
Okay. Ashlyn? Growth or decay on this first one? Ashlyn. Growth. What were you looking at to determine growth, Ashlyn? The number in parentheses, the one that is the base of the exponent, right? 1.4 is greater than 1, therefore it is growth. Izzy? Growth or decay?
Decay.
Okay. Excellent. And you are looking at which number? The number in the parentheses, 1.4. Okay, Chloe? Growth or decay? Why do you say growth? Because that looks like a fraction to me. Because it's improper. Okay. She got nervous, like, why did I ask that question? Is she wrong, right? Okay. But be on the lookout for that. Like an improper fraction, sometimes people like immediately say decay, but that's actually more than one. Okay, excellent. So that's growth. And then, Dylan, what'd you guys say for the last one? Decay, because you're looking at what? 0.89 is less than 1, but it's more than 0, so it's a decay. Okay, excellent. So on these, you don't look at any part of the A value. You wouldn't look at anything else other than B, whatever the exponent is touching to determine growth or decay. Excellent. Now, let's graph a simple function to see what the basic shape of our graph will look like. We're going to do y equals 2 to the x. What do you think might be helpful to us when we're trying to create this graph for the first time? Oh, a table. Yeah, we would like some points to graph, wouldn't we? We don't know what it looks like. Okay, so let's make a table. X, Y. Since this is my first go-round with the exponential function, I'm going to make my table kind of big so I can check some different numbers and confirm that I agree it looks the way it should. Okay, what kind of numbers do you guys want to put into this equation? Okay, you say -1, -2. I heard 7. 0. 1, 2. Okay, I would say those are probably like the normal ones, but I actually like that we're putting in 7. Okay, so let's plug them in, and this is kind of like where we see the warm-up practice. Let's do it without our calculators. Let's just give exact values. We can do it, right?
So the first one's going to be
What? No.
What?
Remember, negative exponents don't make things negative.
Oh, they make
Flip
this
side.
action.
So instead of -4, Mason, you would say, awesome. Oh, that's something Mr. Simpson said. The baby goes in the basement. Or
Yeah, you told us it.
I don't know it. No, it's Mr. Simpson.
Yeah,
Yeah.
you told us that, Mr. Simpson.
Oh, they said to put the baby in the basement. Does anybody know what I'm saying? I don't even know what I'm saying. But yes, you're right. Put the baby to bed or whatever. Okay.
Sounds like you should
2
be
to
killing
the negative 1.
1.5.
2 to the 0. Oh, thank you. 1. Anything raised to 0 is equal to 1, right? Don't forget that. 2 to the first. 2, 2 squared 4. 2 to the 7th.
128.
Cheater.
Okay. Okay, so I'm drawing myself a little coordinate plane. You know, Kaylee gave us 128 for x equal to 7, and I'm going to keep that in mind when I'm graphing, but I'm probably not going to plot that because that one's too big. So know that if you, like with exponential functions, you're going to get some really big numbers sometimes. So you either might need to scale your graph if they're all really big, or you could decide to leave off some of your points if you wanted to. Okay, well, graphing -2 1/4, that means I'm going to go left 2 and up 1/4, which isn't very much. So I'll just put it right there, close to the x-axis. I didn't give myself a whole lot of space right there. And then I'm going to do -1 1/2, so I'm going left 1, and I'm going to go higher than 1/4, but only halfway, right? So we can plot fractions. It's like just go in between 0 and 1. 1/4 is less than 1/2, so that one should be lower. And then when I get to 0, 1, that one's easy to plot. 1, 2, and 2, 4. I sort of put a, I probably shouldn't have added that extra tick mark, but I did. Okay, so, it's going to bother me. How about that? 2, 4. Okay, and then like thinking ahead to Kaylee's 7, she gave us the value of 128, right? That's like off my board, so that's up here. So do I have a pretty clear understanding of what's happening to the right of my graph? Yeah, it's going way up, right? So I'm just going to like start at this -2 1/4, and I'm just going to be like, here we go. That's exponential. Okay, now the other thing that we want to think about is what's happening on the left side of the graph.
Sorry.
Well, it isn't actually starting. I just like didn't go any further than -2 because we don't have any points left of -2. So let's say you pick some other points that are left of -2. What do you want to pick? -12. I like that. Okay. So I'm not actually even going to evaluate this one, even though I could. I'm going to say 2 to the -12 is 1/2 to the 12th, which already 2 to the 7th is a large number. So I'm going to say this is 1/, a big number. Are you okay with that? Just for like this? And like, as I go more negative, isn't it just like bigger and bigger and bigger? So what happens to 1/, big numbers?
They just get more.
Well, they stay positive, don't they? But they get smaller and smaller. It's like cut up your Snickers bar into smaller and smaller and smaller pieces, and then you get one piece. Not much Snickers at the end. Okay? So, can you imagine an exponent that we would put in for x and get 0 out? No. Because every time, think about like 2, and then you put in a negative number. That's 1/2 to a negative number. And it doesn't matter if I cut up your Snickers bar into 1,000,000 pieces. And I say I'm going to give you a piece. You still have a piece, don't you?
Yeah.
That's the whole thing about the guy walking to the door halfway, right? And you're like, Miss Cronky, you're at the door. Stop. It's like, okay, you've cut up my Snickers into the smallest atom molecule whatever, we don't even see it, we're not really getting Snickers, right? But mathematically, do you ever get to 0? No. So when you draw, you're going to have to be really careful. When you draw your graphs, I call it hugging the axis. You just get really, really close to it. You just sort of ride along right next to it, but you never ever touch it and you never ever cross it. Okay? Yeah, that's a good one. Okay, this is exponential. Now, another thing that I'm going to want you to do on your graphs is draw this line that we're getting really, really close to but never touching. And it has a special name. Does anybody know what that line is called? You get really, really close to it and never touch it?
That looks like a parabola.
It's no.
Or a half parabola. Where you graph, exponential.
Okay, draw this in your notes. Yeah, I get what you're saying. Draw this in your notes. So I'm going to want to see this on your graphs. This dotted line. I draw it as a dotted line because it's not part of the graph. It's just like a line that's there that like my graph doesn't cross. So you're going to draw this line that we get really, really close to, but you're going to make sure you never ever cross it. Okay? And that line is called an asymptote. An asymptote. An asymptote is a line that a graph approaches but never touches. All exponential functions have asymptotes. That goes back to the nature of what you're doing with exponential functions. When you put in those negative numbers, they don't actually make it negative. So we can only get really, really close to, in this case, 0. Now that's going to change when we do shifting of our graph. Okay. But for right now, we're just going to get really, really close to 0 and never touch it. Now, I do have approaches in gold with a little asterisk there. And what I mean by that is the place where you're actually approaching the asymptote, it's always true for exponential functions that we're never going to cross it. We're going to get really, really close. I call it hugging the asymptote. We're never going to cross it. It's always going to be true for all exponential functions. However, in Chapter 7, we're going to talk about something called a rational function, which also has asymptotes. And there can be some more complicated rational functions where you actually cross the asymptote, but on the far side of your graph, you just get really, really close to it. Okay? So this is not this chapter. Okay, so don't worry about it right now. But probably the most common thing that people will experience is when they get to pre-calculus. They might have a graph with 3 parts, and it has a vertical asymptote. Well, actually, it has 2 vertical asymptotes. It has a horizontal asymptote. See, I labeled it here, but my graph actually crosses a horizontal asymptote in the middle. But that's fine because it's hugging the asymptote on the left and it's hugging the asymptote on the right. So that's what I mean by saying the far end of the graph. Like the end behavior for a polynomial. Remember that polynomial could go up and down in the middle, but on the ends, its arms was like rise, rise, fall, fall. So we're talking about end behavior when we say asymptotes. But please note, all exponential functions will never cross the asymptote. So if you draw your graph crossing your asymptote, it's bad. Shouldn't happen. And that P is silent. So it's like asymptote, not asymptote. Asymptote. Let's do y equals 1/2 to the x.
Oh, this is gonna be decay.
How did you know right away it was going to be decay, Mason?
Because the base number is less than 1.
Very good, very good. Okay, well, we probably want to start with a table of values. Now that we kind of have an idea of what's happening, when you guys are graphing on your homework, you probably don't need all those extra points we did. So I like the -2, -1, 0, 1, 2. I think this is satisfactory for tonight. Okay, what happens when you take 1/2 and you raise it to the -2?
Does it become a non-fraction?
It becomes a non-fraction. So now it's 2 squared, which is 4. And then 1/2 to the -1? 2. 1/2 to the 0? 1. 1/2. 1/4. So I can plot those points: -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. Where is your asymptote going to be again? At the x-axis. I mean, you could think about this like going forward. Like if I do 1/2 to the 10th, 1/2 times 1/2 times 1/2 times 1/2 times 1/2. Or if we take a Snickers bar and we keep cutting it in half, it just gets smaller and smaller, but it never theoretically disappears. So you should draw your asymptote. And then when you draw your shape, make sure it doesn't cross your asymptote. Just hug the line. Okay, now, I am going to want you to practice a few things. Domain, range, asymptote.
Asymptote.
It's good. I don't mind if you guys say it a million times, because if you remember it and you say it correctly, I'm cool with that. Okay, what kinds of numbers can you put in? Like, what's allowed for x?
X equals.
Oh wait, I mean.
Anything, right? I mean, this arrow is going to the left, this arrow is going to the right. We can put in negatives, we can put in 0, we can put in positives, and we always get answers back out, right? So we would say x equals all real numbers. Okay. What kinds of numbers do you get out for y? Positive. So we're going to say y's greater than. Okay, they can be 1, but can they be less than 1? Yeah, we've got all those really, really small fractions. And remember, we're thinking about that idea of like 1 over some really big numbers is still something, not nothing. So it's got to be more than 0, but it's really, really close to 0. So y is greater than 0. Wow, that's a crazy 0. Sorry. Okay. And then what would you write for your asymptote? It's a line. You could say it is the x-axis, but I want you to write it as the equation of a line. So how do we write the x-axis as the equation of a line? Y equals 0, essentially. I mean, you could do mx plus b, but what's the slope? You're on the treadmill like this. What's your incline? 0. A horizontal line has slope 0, so then it's just going to be 0. Okay, now, if I go back to my growth graph, what would you say for domain, range, and asymptote? All real numbers for domain. Range will be y is greater than 0. Y equals 0.
So it's the same for all?
So yeah, until we start shifting things, it will always be true. Now, can you imagine, like, what kind of shift will change our asymptote? A vertical shift. If you make your whole graph move up 5, then your asymptote moves up 5.
What if your graph moves down?
And then your whole graph would move down, so your asymptote would have to move down. Can your graph move left and right?
Yes.
Yeah. Would you notice a change in your asymptote?
No.
Okay.
Okay.
Is that gonna be hard?
I will hope not. Okay, so these are going to be problems like on your homework, graph, state domain, range, and asymptote. You know, you're just starting with a new base. Okay, so you can, I would say, actually, you could probably even get by with like -1, 0, and 1. Right? 1, 4, 1, 4. You know what the graph looks like. So I won't do all of this. I just want to kind of show you what I expect on your homework. -1, 1, 4, 0, 1, 1, 4. You should draw in your asymptote. I want to see that. And then don't cross your asymptote. And I want you to practice, I don't think the book says it, but I want you to practice domain. X equals all real numbers. Range, y is greater than 0. Asymptote, y equals 0. That will make transforming them a little bit easier, at least. Practice it now. Okay. Now, can you imagine, like, what do you think this graph is going to look like? How's it going to be different than the blue graph I have on the left when I do point to the x? What, smaller, what'd you say? What do you mean by that, smaller incline? Yeah, so that's like one of the key things for you to start thinking about is like, what's the difference between the shape of the decay and the growth? This was a decay, right? When Mason said the B was less than 1. Is it dramatic at some point? Yeah, it's dramatic over here on the left where it's like dropping really fast. And then what happens? It hardly drops at all. You don't even notice it. So when we talk, this is going to be weird because we don't have any reflections yet, but exponential growth does not mean increasing, and exponential decay does not mean decreasing. What we're referring to is our rates of change. The rate of change, so when you're talking about incline, think about slopes between points. If you were just checking the slope between 2 points, the slopes are getting smaller and smaller until you don't even notice the slope changes. It looks horizontal. And then if you have something that's exponential growth, what's happening to your slopes? They're getting bigger and bigger. So that's really the difference between exponential growth and exponential decay. Okay. All right. Here is your homework assignment. I just want to clarify. So it says like 3 through 20 evens. That means I'm expecting tomorrow when I come around to see 4, 6, 8, 10. Okay. So you can do the odds if you want. I had been assigning odds, and I think odds are great because you can check in the back of the book, but I also want to make sure people are really doing their homework. And then I got some good, like, thoughtful questions there at the end. This will go away.